Thank you for this opportunity. Especially, it's a privilege to have an opportunity to present the talk at first. So today I am going to talk on how to extract Hawking temperature of dynamical black holes via conformal transformations. Basically, so this was the continuation of our work on extracting the Hawking temperature of dynamical black holes, and on our previous work we used Rindler transformations, and in that work, so we analyzed, we took the near horizon region of black holes, and in the near horizon region we did Unruh Hawking analogy, or especially took the reference of uniformly accelerating observer, and based on that, so we extracted the temperature. So basically, so the motivation and the next logical step of this talk is as follows. So we are first talking about the background. So why we talk about dynamical black hole, and on dynamical black hole, so we take a specific example, specific dynamical metric. So why we take that metric? So basically, we study or we try to find semi-classical self-consistent solutions to find the near horizon region. So to find the solutions of ultra-compact objects. So what are the solutions, or what is the generic solutions on semi-classical gravity? So that contains horizon on ultra compact objects. So we first discuss about that, and then so after like obtaining solutions, some of the solutions on semi-classical gravity, so we see like, or we try to find if there are some dynamical solutions which are non-trivial one, and which are relevant, or like which are popular in literatures. So indeed there are, and then on some particular solution, on a particular solutions which is of specific interest, we try to investigate Hawking radiations and the thermodynamics. So basically we first talk about physical black hole solutions in semi-classical gravity, and indeed the Vaidya metric or Vaidya spacetime, which is the spacetime of evaporating black hole, falls onto that category. So we take the particular model of linear Vaidya spacetime to study Hawking temperature and the thermodynamics. So let's start first with physical black holes. Our first, like, we work in metric theory of gravity. So we here like specific our discussions to spherically symmetric spacetimes, and on that spherically symmetric spacetime, so we can write metric in this way. So this is the most generic metric in spherically symmetric spacetimes, and this is like in what we call Schwarzschild coordinates. If you look carefully at this metric, so this has two arbitrary functions, and like so, basically two arbitrary functions constraining these two independent functions are sufficient to constrain the metric in spherically symmetric settings, and these two functions completely characterize the spacetime geometry. And another thing to notice here is like we are writing in this like familiar form, which we basically see in any spherical coordinates, in Minkowski spacetime, and this like familiar forms of angular variable has the metric like radial metric as metric r, and we call that coordinate as areal radius. And that areal radius, writing metric in this form, allows us to characterize so this function in coordinate independent way. And if we define this function in this way, so we call this m, which arises from coordinate independent way, as Misner's short mass. And so of course, like this metric is coordinate dependent thing, but like a general spherically symmetric spacetime, in general spacetime we can construct invariant quantities, and we here focus on invariant quantities which are derived from Riemann curvature tensor, which is basically constructed from metric and its derivative of the second derivative. And so we can construct a lot of like invariant quantities, and depending on the generality of our spacetimes, like spherically symmetric spacetimes or axially symmetric spacetimes. So some number of these quantities are sufficient to constrain, sufficient to sufficient to constrain the space-time geometry or characterize the space-time geometry. So we talk about physical black holes and we talk about horizon. So let's us first introduce like what we mean by horizon. So basically, one of the most popular notion of horizon is event horizon. And when we talk about horizon in static black hole settings, so that horizon means event horizon. So that is the boundary where like from which like the outside observer is not affected by the phenomena occurring inside in black hole settings, but like there are event horizon in cosmological settings also, which we don't talk here. Although like our like specific semi-classical settings applies to cosmological settings also. So basically, by this definition, so event horizon is a global teleological entity, which means that like one needs to understand the entire history of the universe to find its location, and for it. So in that sense, event horizon is unobservable because like any mortal observers has no like that long amount of time to track its locations. And thus like for practical studies, so we focus on another characteristics of black hole. Basically, so by definition of black hole, so what we mean is dragging back of light, and that dragging back of light so can be expressed mathematically using the notion of closed trapped surface, like from which like light cannot escape now or at present. So we don't know about future. So physical black hole is an object containing that closed trapped region from which like light is dragged back or pulled back, and the outermost like boundary of that trapped region is called apparent horizon. For the metric we have shown before, for general spherically symmetric metric, the apparent horizon is located at r equals twice m, which is important for later calculations. Another thing is we define another new notation T mu nu, which we don't say an energy momentum tensor here. We just denote this. We just write it to denote Einstein tensor, which is the quantity on right hand side. And in spherical symmetry, so there are like a lot of curvature invariants, and there are works which has shown that like 16 of curvature invariants. So if you consider perfect fluids is sufficient to completely characterize any like general metric. So deriving from where like if we consider energy momentum tensor as perfect fluid, but spherical symmetry is very simple case, and 3 of the curvature invariants are sufficient to constrain the geometry, spherical symmetric geometry. And among 3 of the curvature invariants, 2 of them are here. So one is basically contraction of this thing, Einstein tensor with g mu nu, and another is its square. We can write them as individual components in these different ways. And if we notice here, the denominator has quantities which goes to 0 at horizon, so based on the definition of apparent horizon. And if this quantity goes to 0, so for curvature invariants to be finite at the horizon, so we should have some constraint on the quantity in the numerator. Basically, they must be equal in the order of calculations we are considering. For these curvature invariants to be finite. So first thing is we demand finiteness of these curvature invariants, and another thing is we demand that this equation holds true. Basically in semi-classical gravity, so this equation is conservation equation, but this time we are not considering this T mu nu as energy momentum tensor, so this is just Einstein tensor. And these equations in semi-classical settings going to be true means that Baingi identity is satisfied here, and this thing is completely generic to all metric theories of gravity. So if we substitute the first equation of the metric I have shown onto this equation. So we have only two non-trivial equations in spherical symmetry, and so of course we have only two non-trivial equations, but we make some more assumptions as we are focusing on near horizon solutions. So we assume that perturbative solutions exist near horizon, and we take the following answers to constrain this one of the variable in terms of this function. So near horizon expansion, we assume that this form of near horizon expansion exists. So now, like substituting these answers into these two non-trivial equations we have got from that Bianchi identity. So we obtain only one independent equations, and this independent equations has this form, which is like not which cannot be solved exactly, but it's not necessary to solve exactly, in the sense that we are focusing on near horizon solutions and we are doing perturbative expansions near horizon. So even like getting exact result doesn't make sense. So if we have only one independent equations, we have started with answers with two independent functions. So we don't have enough number of equations to determine exact value of beta. So if we look at beta here, so this is the power of near horizon expansions. But what we know is like we are focusing on the solutions with horizon. So like as we approach horizon, as r goes to twice m, which is like approaching horizon, so the quantity must go to 0. So for that answer to go to 0, beta must be greater than 0. So that's the only constraint we can say about beta. And so if we impose static limit on these differential equations, we have these specific solutions. So static black hole solution in any metric theory of gravity should preserve Schwarzschild form. So should be written in this form, otherwise it would be inconsistent with the Bianchi identity and the assumption of regularity of curvature invariance. Now just they are demanding, so not constraining only to the static solutions, but demanding or focusing on the dynamical one. We have this specific form on the first function based on the second function based on the answers on the first function.
Pravin, but that's true. That's true only near the horizon.
Yeah, that's true only
it's
near
the horizon.
It's not
a general relation.
No. Because like we are starting from finiteness of curvature invariance, and we are like focusing already on the near horizon on that assumption, and on second assumption which we are taking specific perturbative expansion on these answers are r minus twice m. So this is only valid near horizon, and from this solution we can see that like RG, so because of this plus minus sign, so we have one is accreting and another is evaporating solutions, growing and shrinking solutions. So the near horizon form of the metric in general settings is this form. So we have now constrained as much as we can based on that identity, and so on literature, so recently work on quantum gravity and like finding so perturbations based on quantum gravity. I have seen solutions, dynamical solutions, which does not satisfy this form, and I think like based on this assumption and working here, those solutions are not even compatible in the semi-classical gravity. So so does that solutions or is that solution compatible with any of the solutions known or popular solutions in the literature? Surely they are, in the sense that like we have Vaidya metric, which represents dynamical black hole solutions based on the collapse of null shell or like evaporation of null fluids. So that falls into this category. And if we write Vaidya metric, especially in advanced coordinates, so it takes this form. So this is linear Vaidya metric, And we can do, so in linear case, in linear evaporation case, we can do exact coordinate transformation. So we have coordinate transformation relationship to write this metric into the form I have shown before, or like explicitly this form, so it's compatible. And moreover, like in the limit of small evaporation, so by using Einstein equations, so not possible in this framework, but by using Einstein equation, we have shown that Vaidya spacetime solves a very good near horizon approximations under some assumption. So comments on that. So our calculations does not particularly rely on specific metric theories of on any specific theory of gravity. So it's valid in all metric theory of gravity. So I have seen specific interesting example. For example, in rational gravity, people consider that like the divergence of EMT is not valid, and it starts from that assumption. What if like divergence of energy momentum tensor is not valid? However, like our theory or like our framework is applicable in that case also.
Okay. So sorry, divergence, you mean divergence is not zero?
Yeah, divergence is not zero. Yeah, oh no, not Bianchi. Conservation of energy momentum tensor is not valid. But even like that is the metric theory of gravity. So Bianchi should be valid. And what I have seen from their solution is like it's hard to find dynamical black hole solutions in other metric theories of gravity. But like on their static black hole solutions also, they have taken the specific form of the metric which is compatible with the metric like I have shown before for static black hole solutions. So far so good here. Now like to analyze the evaporation thermodynamic property or like Hawking particle production in this semi-classical framework in these settings. So we take a specific example of linear Vaidya. So because it is the simplest non-trivial solutions following from semi-classical gravity, and this linear Vaidya space-time, so it's like a very interesting property that it is conformal to some static space-time. So if we have some static space-time, and if we multiply that static space-time by some conformal factor, then we have linear Vaidya space-time. And if we have some static space-time, we can calculate event horizon of that static space-time. Although event horizon is a global concept, so not a local concept, not even quasi-local concept, but we can calculate event horizon in static space-time. And this conformal transformation has nice property that it preserves event horizon. So this event horizon is also the event horizon of linear Vaidya metric. This notion of event horizon is imported in calculation of Hawking radiations. And another thing we need or we can generalize in these dynamical settings based on conformal transformations is the notion of killing vector. So what are killing vectors? So killing vector are infinitesimal generator of isometries, that is vectors like which preserves metric. For example, in static metric, so static metric is independent of time coordinates. So if we do any time translations, the metric doesn't change. So time translation is the killing vector of static metric. So this can be generalized. This example can be generalized. So one can introduce the notion of conformal killing vector in dynamical space-times based on the killing vector in static space-times. So that conformal killing vector is basically the killing vector of corresponding conformal static space-time. For example, on linear Vaidya metric, this particular example which we are referring to again and again has this form of conformal killing vector. This is written in advanced coordinate and this is in static coordinate. And in static coordinates, it's clear that this is just some time translation vector. So from this conformal killing vector, we can define another notion of horizon, which is conformal killing horizon. And in static space-time, this conformal killing horizon basically coincides with event horizon. So, and event horizon is does not change on conformal transformation. So this horizon just event horizon in this our dynamical case also, our dynamical settings. When we talk about particle productions, we start with generally Penrose process and superradiance and the possibility of particle production in core spacetime, and then we go to spherical symmetric case and see how particle production happen. But like this Penrose process, if we talk about dynamical spherically symmetric settings, we can generalize to, or we can construct analogous process in spherically symmetric spacetime also. So to explain Penrose process in spherically symmetric spacetime, we need so the notion of Kodama vector. So what is Kodama vector? So in spherically symmetric spacetime, there exists an observer, like spherically symmetric observer, which respects the symmetry of the spacetime. And based on that observer, one can define a geometric quantity known as Kodama vector. So this vector is time-like outside the apparent horizon and space-like inside it. And up to normalization factor, Kodama vector coincides with Killing vector whenever both exist. So this is just the generalization of Killing vector to dynamical spherically symmetric cases. And if we have Kodama vector, then we know like Kodama vector is time-like outside horizon and null inside and space-like inside horizon. So in spherically symmetric dynamical spacetime, there exists a region between the event and apparent horizon, which we call quantum ergosphere, and in that region it is possible. In that region, since like it is between apparent and event horizon, particle can escape from that region. However, particle could also have negative energy in that region because Kodama vector could have is space-like in that region, and because of that, like some physical form momenta, some particle can have negative energy in that region, and thus we can import the phenomena of Penrose process in this dynamical spacetime. Penrose process of axially symmetric case into the spherically symmetric case in dynamical black holes. 5 minutes, okay, thanks. And after that, so this possibility of like superradiance like process in spherically symmetric case, so we turn into a particle production. So let me skip this and just mention that like if we consider field equations in Minkowski spacetime, we can expand field equations into positive and negative frequency modes, and these modes are specifically well defined in Minkowski spacetime in flat spacetime settings because of the existence of global time-like Killing vector. However, in chord spacetime, so this decomposition has no meaning because like so there doesn't exist these unique decompositions. We can decompose in like different ways, and but however like we still like mathematically we still do these decompositions, and the functions, the modes fk and fk star, it's possible that they could form a complete basis of solutions in chord spacetime. So let's take the field equations like in flat spacetime in this chord spacetime settings, and as we are considering conformal case, conformal case. So if we transform metric in this way, and if we transform the field in this way, these field equations remain unchanged. So to find the explicit solution of the field equations in linear Vaidya background, we first find the solutions in static background, and thus like we have reduced the problem of dynamical problem into static problem, and we will solve in static background, and we will by these conformal transformations transform into dynamical case. Apparently in that static background, field equations was exactly solvable and can be reduced to Hune differential equations. So this is the incoming mode, which is different from Schwarzschild case, but outgoing mode is not so different, and one can express outgoing mode in terms of incoming modes. So outgoing functions in terms of incoming functions because like they form complete basis, and from that one can extract like by Fourier transformations, one can extract these alpha and beta coefficients, which are Bogoliubov coefficients. So I'm not going to talk about this, but what I am going to say is we can exactly solve Bogoliubov coefficients, and we can write the Bogoliubov coefficient in this form. So two Bogoliubov coefficients by solutions or by calculations. And based on that, so if we have relations between two of the Bogoliubov coefficients in this way, we can extract Hawking temperature for Vaidya geometry, and that temperature we can see here is constant, which is very surprising thing. But like it's not a surprise that various people has proposed that like the temperature in Vaidya background should be constant, and they have related that to geometric surface gravity and calculated geometric surface gravity explicitly, and they have found exactly this quantity. So just to say in context of figure what happening, so this is the section of the static diagram, and this whole section contains is the Vaidya diagram. So after evaporation, so what we are seeing as constant temperature is observed by the observer here, and if we like extrapolate that like to the observer associated with scribe plus, then that temperature like won't necessarily be constant. So we need to renormalize that constant temperature, rescale and renormalize that constant temperature to obtain the temperature observed by observer at infinity on Vaidya background, and that will be 1 over 4 MV. And yeah, so this was just the literatures which were talking about temperatures on dynamical backgrounds, on conformal, on dynamical background which are conformal to static spacetime, but without exact derivations, some speculations. These were the papers talking about that, and our like result matches with this result, or like their speculations or their thoughts, their arguments. And this is my conclusion. So basically, thank you. So I'm extremely sorry that last half was a bit rough, but still.
Yes, a couple of interesting things. So, I'll have to poke your brains about any specific questions. Okay, so then let's thank Pravin, and Ryan have to start setting up.